Welcome back, aviation enthusiasts, to another exhilarating episode of our journey through the boundless skies. Today, we delve deeper into the realm of flight, uncovering the marvels of unconventional and groundbreaking aircraft that push the boundaries of traditional aviation. In 2004, renowned director Martin Scorsese released the feature film The Aviator, which garnered 5 Oscars. This cinematic masterpiece sparked widespread interest in one of America's most extraordinary figures, billionaire Howard Hughes. Among his many ventures, Hughes undertook the ambitious project of creating a colossal amphibious aircraft known as the Hughes H-4 Hercules. This flying boat, constructed as a singular prototype, made its historic maiden flight on November 2, 1947. Despite only completing a single flight, Hughes's Hercules secured its place in history as the largest flying boat ever built. Its monumental wingspan of 98 meters remains unrivaled to this day, surpassing even the dimensions of aircraft such as the AN-124 Ruslan and the AN-225 MRIA. During the early stages of World War II, Allied forces initially underestimated the threat posed by Nazi Germany's submarines. Lessons from World War I had been disregarded, leading to catastrophic losses in naval trade. While losses from German submarine attacks were initially manageable during 1939 to 1940, the situation escalated dramatically in 1941 to 1942. The German Kriegsmarine unleashed a reign of terror across the vast expanses of the Atlantic, sinking nearly 700 Allied ships in the first 7 months of 1942 alone. It wasn't until the latter part of 1942 that the situation in the Atlantic began to improve, primarily due to a significant increase in the number of escort ships deployed to protect convoys. This concerted effort helped mitigate the threat posed by German submarines, albeit after considerable losses had already been incurred. Despite these actions, the threat from German submarines was not eliminated. In such conditions, the idea was born that would protect valuable military goods from Kriegsmarine attacks. Cargo could be shipped across the Atlantic Ocean not only by water, but also by air. However, the implementation of this idea would only be possible with the creation of a transport plane of sufficient carrying capacity. To address the pressing need for a solution, shipbuilder Henry Kaiser proposed the design of a large transport flying boat. Renowned billionaire and aircraft designer Howard Hughes enthusiastically took on the challenge of bringing this concept to fruition, resulting in the creation of a giant aircraft that remains unparalleled to this day. In 1942, the US government contracted Howard Hughes to construct a single prototype aircraft, driven by the vision of a sizable flying vehicle to support naval operations. The result was a multi-ton wooden amphibious aircraft with a remarkable wingspan of almost 100 meters. Initially designated as the NK-1 Hercules, this flying boat boasted impressive dimensions that continue to impress. A fuselage spacious enough to accommodate over 700 soldiers, weaponry, and approximately 60 tons of commercial cargo. To provide the necessary power for this colossal aircraft, 8 engines were installed in its wings. The project's development was guided by a specific goal: to construct an aircraft for cargo and passenger transportation while minimizing the use of strategic raw materials. Consequently, the decision was made to build the aircraft from wood rather than aluminum. The envisioned role for this flying boat was to transport troops and various cargoes from the United States to war-torn Europe along a secure air route, circumventing the threat posed by the German submarine fleet. Working documentation for the new flying boat was developed very quickly, which cannot be said about the pace of the aircraft construction itself. The works that began in 1943 were fully completed only by the middle of 1947. This slowdown in the construction of the aircraft was influenced by several reasons, ranging from the end of the Second World War, as a result the military lost interest in this car, and ending with various legal proceedings against Howard Hughes. Disputes regarding the funding for the project persisted throughout its execution, reflecting differing opinions on its necessity. One dissatisfied US senator famously referred to the future amphibious aircraft as a flying forest warehouse, but it garnered another well-known nickname, the Spruce Goose. A substantial sum from the US state budget, totaling $22 million, a considerable amount for the time, was allocated for the project's implementation. However, this funding proved insufficient, prompting Howard Hughes to personally invest an additional $18 million into the endeavour. The flying boat, subsequently renamed the N-4 after Henry Kaiser's departure from the project, marked the fourth aircraft of Howard Hughes's own construction. On November 2, 1947, the N-4 made its inaugural and final flight, piloted by Hughes himself. The aircraft undertook a brief flight, ascending to an altitude of 21 meters and traversing a 2-kilometer stretch along the coast of Los Angeles. With this flight, the saga of the Hercules nearly came to a close, transitioning abruptly from the realm of active aviation to that of a museum exhibit. Ultimately, this costly and sizable flying boat proved to be of little practical use at the time. The Hughes H-4 Hercules was characterized by a hull, a cantilever wing, and 8 radial engines. The flying boat had a vertical and tail plumage, as well as fixed wing floats. The entire structure of the aircraft consisted of laminated wood, but contrary to the nickname in the construction of the flying boat, it wasn't spruce, it was birch. At the Howard Hughes plant, woodworking was able to achieve high aviation standards. The construction of the aircraft involved creating full-size patterns of structural elements, from which matrices were produced for molding the parts. The thinnest piece, with a thickness of 1.2 mm, consisted of 3 layers, each 0.4 mm thick. Conversely, the thickest part measured 254 mm in thickness and comprised 200 layers of veneer, each 1.27 mm thick. To maintain the integrity of the veneer layers during gluing, double-capped nails were utilized. Once the glue had set, these nails were removed using a special nail puller, resulting in the extraction of approximately 8,000 nails across the entire flying boat. The resulting holes were then sealed with a specialized putty. Following assembly, a thin layer of primer was applied to the surface, succeeded by a layer of rice paper and 2 coats of protective lacquer. The exterior surfaces of the aircraft were coated with aluminum paint, concealing the fact that the aircraft's underlying structure was composed of ordinary wood. Both the aircraft's skin and its structural components appeared as if they were made of aluminum. The cargo compartment of the amphibious aircraft featured 2 levels, interconnected by a spiral staircase. Hinged doors located at the nose of the aircraft facilitated the easy passage of 2 railway cars or a Sherman M4 tank. This design ensured the versatility and practicality of the aircraft for transporting various types of cargo. At that time, the Hughes H-4 Hercules was the only aircraft that was able to transport the tank through the air. In the best traditions of submarines and ships, 18 seal compartments were provided in the design of the seaplane. 6 of them were enough to keep it afloat. The electrical equipment of the aircraft operated from direct current with voltage 120B, since with traditional 24B, the cross-section of the wires, the length of which reached 50 kilometers, was very large. The seaplane was to be lifted into the air by 8 huge radial air-cooled R4360 Wasp major piston engines from Pratt & Whitney. Each of these engines developed 3,000 horsepower. The engines of the aircraft were equipped with 5-meter 4-blade propellers. Of the 4 engines positioned closest to the fuselage, 4 were capable of generating reverse thrust, granting the giant aircraft the remarkable ability to maneuver independently in reverse and execute tight turns. The expansive size of the flying boat facilitated in-flight engine repairs, as special passages within the enormous wing allowed access to the engines. At the point of attachment to the fuselage, the wing section reached a height of 4 meters. Despite its unprecedented scale, only a crew of 3 individuals was required to operate the aircraft. The collaborative effort between Hughes and Kaiser aimed to produce the largest aircraft ever constructed, surpassing any previous aircraft in size by a staggering 7-fold. This ambitious project stands as one of the most remarkable endeavours in aviation history. The determination and valour of Howard Hughes and his dedicated team, who persevered despite numerous challenges, culminated in the historic flight of the H-4 Hercules. However, tensions arose within the project leadership, leading to significant contradictions. Henry Kaiser advocated for the construction of a 70-ton aircraft to adhere to deadlines and present a finished product to the military. Conversely, Howard Hughes insisted on building a 200-ton airplane, necessitating greater investment of time and resources. This discord ultimately led to Kaiser's departure from the project, while Hughes became increasingly enamored with the idea, incorporating new improvements and proposals that further prolonged the construction timeline of the flying boat. As a result, in 1942, this order was urgent for the US government, but by 1944 it lost its relevance. By this time, the situation on the fronts of World War II had changed radically, and the interest of the United States in the project gradually faded away. The US government had contemplated cancelling the contract for the seaplane's construction, but by then, Hughes's motivation had transcended mere practicality. He had become consumed by the idea of creating a cargo aircraft that would surpass even the most extravagant imaginations of his contemporaries. On November 2, 1947, the Hercules was launched, and Hughes, alongside his small crew, initiated the aircraft engines for the first time. Following several water taxi tests in front of a sizable audience, predominantly journalists, the flying boat lifted off from the surface of the Los Angeles harbor without any prior announcement, embarking on its inaugural and final flight. Maintaining an altitude not exceeding 20 meters, the Spruce Goose traversed approximately 2 kilometers at a speed of 120 kilometers an hour before executing a flawless landing. This unauthorized test flight, undertaken in defiance of an official ban on taking the plane airborne, served to silence numerous critics of the project, demonstrating that the largest aircraft in history was indeed capable of flight. Many regard this flight as one of the most significant moments in the annals of aviation history. Following its historic flight, the Spruce Goose returned indefinitely to its hangar, a colossal structure specially constructed to house it and prevent it from ever taking flight again. At Howard Hughes's behest, until his passing in 1976, the flying boat remained in a state of perpetual readiness, with its engines started every month. Initially, a team of 300 individuals monitored the aircraft's condition until the 1950s, when the staff was reduced to 50 people. Nevertheless, the annual cost of maintaining the air giant in flight-ready condition amounted to approximately $1 million. Additionally, the construction of the hangar where the Hughes H-4 Hercules was preserved for eternity incurred costs of around $2 million. Currently, this unusual aircraft is an exhibit at the Aviation Museum in McMinnville, Oregon, where it was transported in 1993. At the same time, over the past 50 years, this flying boat has become one of the most beloved artifacts of the United States, moving from a state of almost total uselessness to the category of object of cultural heritage. Today, the story of the Hughes H-4 Hercules, which soared into the sky only once in its lifetime, is revered as a testament to its creator's unparalleled resolve to see the project through to completion, transforming the aircraft into an emblem of the 20th century. Regarded as a symbol of determination and ingenuity, the Spruce Goose continues to captivate the imaginations of people worldwide. Drawing over 300,000 visitors annually, the aircraft stands as a living testament to Howard Hughes's extraordinary vision and perseverance. Its towering presence serves as a reminder of the boundless ambition and unwavering commitment that characterized an era of pioneering aviation endeavors. Through its enduring legacy, the Hughes H-4 Hercules remains an enduring symbol of human achievement and innovation. Throughout the history of military transport aviation, developers of new projects have consistently aimed to enhance aircraft and helicopter capabilities, including increasing carrying capacity, speed, and range of flight. However, there's also been interest in light or ultralight vehicles, capable of aerial transportation for small loads or passengers, catering to specific needs. Over different periods, numerous projects in this category have emerged. For instance, one of the early endeavours to create a flying jeep for military applications was the development of the XV-8 Fleep by the American company Ryan. In response to the diverse transportation needs of the military, including the requirement for aircraft capable of transporting light loads or small groups of personnel, Ryan Aeronautical Company initiated work on its version of such an aircraft in the late 1950s. This project incorporated several innovative ideas aimed at reducing the weight and size of the structure while meeting the necessary flight and carrying capacity requirements. Designated as the XV-8, the aircraft project was informally dubbed Fleep, or Flying Jeep. However, official military documents refer to it as the FWAUV, Flexible Wing Aerial Utility Vehicle. In other words, auxiliary air transport with a flexible wing. Notably, the official designation mirrored the aircraft's goals and fundamental design features, while the informal name encapsulated its operational essence. To achieve the desired characteristics, the prospective aircraft needed to minimize weight. A solution proposed was to utilize a flexible wing, commonly known as a wing rogolo, to reduce the structure's mass. Back in 1948, Francis and Gertrude Rogolo proposed an original wing design suitable for use in light aircraft. It was originally proposed to use a frame of 3 parts of great length, to which it was necessary to fix a square or diamond-shaped canvas. In the future, a new design of such a wing appeared, featuring a different composition of the power elements and the triangular shape of the canvas. The transition from traditional rigid wings to the Rogolo system in the Ryan XV-8 project was notable for its simplicity and cost-effectiveness in production. One characteristic feature of this aircraft was its ability to control flight by adjusting the relative position of the wing and the aircraft's centre of gravity. However, the flexible wing also had its limitations, particularly in adverse weather conditions, which could restrict its operation in certain environments. Nevertheless, the Rogolo wing later found application in hang gliders. In the XV-8 project, the Rogolo wing was proposed for use, along with several other components serving various purposes. The unique characteristics of the wing, along with existing requirements and new ideas, contributed to the development of a complex aircraft structure capable of transporting people or cargo despite its simplicity. The fuselage of the XV-8 aircraft featured a straightforward design with essential components. A rectangular platform served as the basis, equipped with fixtures for cargo installation. Positioned in front of the platform was a small protruding unit housing the controls and pilot's seat within a nose cone. At the rear of the platform, a frame was provided for mounting the engine. Supporting structures, both in front and behind the platform, were attached to accommodate the unusual design of the wing, with additional components for wing control integrated into these structures. Ryan Aeronautical developed its own version of the flexible wing for use in the XV-8 project, contributing to the aircraft's unique design and capabilities. As a basis for this product, 3 metal pipes with a length of 26 feet, about 8 meters, were used. In the nose of the wing, 3 tubes were pivotally connected, which allowed them to move in the same plane. A special mechanism was used to change the relative position of the pipes of the wing frame, which implies the simultaneous movement of the side parts. Near the central part of the wing was placed a set of rigid beams, with the help of which the side pipes could be reduced to the central or conversely diluted to the sides. At maximum extension, the wingspan of the XV-8 exceeded 10 meters, while when folded it measured 3 meters. To manage the excessive spreading of the tubes, a control mechanism and several braces were employed. The wing structure comprised 3 pipe beams supporting a quadrangular canvas, forming the wing plane and generating lift. Upon extension, the side pipes created the characteristic wing profile with 2 curved sections at the rear. The leading edge exhibited a sweep of 50 degrees, and the total area, excluding canvas bends, measured 450 square meters. Various materials, including synthetic textiles and films, were tested for the canvas surface. Mounted on the central beam of the Rogolo folding wing were attachments for fuselage truss installation. This pipe was firmly affixed to a swinging arm hinged at the apex of the framework. The front arm of the rocker was linked to a system of rigid rods leading to the control post. Using the appropriate lever, the pilot could adjust the wing's angle of attack to suit the current flight conditions. Located at the rear of the fuselage was an engine mounting frame. The power plant employed was the Continental IO360A piston aircraft engine, delivering 210 horsepower, paired with a two-bladed propeller with a diameter of 2.14 meters. During testing phases, the XV-8 Fleep underwent trials with and without engine covers for varying aerodynamic conditions. A substantial fuel tank, contributing to the vehicle's bulkiness, was situated in the central portion of the wing truss. To enhance aerodynamics, a vertical tail was integrated into the design. Mounted on a lightweight beam extending from the engine frame to the fuselage platform, a trapezoidal keel was attached, with its upper section pivotally connected to the central beam of the keel. The beam was designed so that when the angle of attack of the wing changes, the keel remains upright. There were drives to rotate the keel around the vertical axis, which it was proposed to use to control the course. For the transport of goods or passengers in the Project Fleep FWAUV, it was proposed to use the platform in the central part of the fuselage, in close proximity to the center of gravity. The length of the cargo platform reached 2 meters, the width was slightly less at 1.5 meters. The Ryan XV-8 Fleep project aimed at maximizing the reduction in size and weight of the aircraft design, and it appears this objective was successfully achieved. The dimensions of the vehicle were kept compact, with a length not exceeding 8 meters, a wingspan of 10 meters when deployed, and a parking height of 4.4 meters. Folding the wing allowed for a reduction in the overall width of the aircraft to about 3 meters while maintaining other dimensions. The aircraft's own weight was a mere 506 kilograms, 1,115 pounds, emphasizing its lightweight construction. For flight preparation, it was suggested to load 68 kilograms, 150 pounds of fuel into the 6.8 kilogram, 15-pound tanks. With fuel and the pilot accounted for, the minimum flight weight of the flying Jeep was estimated at 658 kilograms, 1,450 pounds. This left a payload capacity of 385 kilograms, 850 pounds, resulting in a maximum takeoff weight of 1,043 kilograms, 2,300 pounds. To facilitate takeoff and landing, the aircraft was equipped with a simple non-removable landing gear. The cargo area between the wing trusses could accommodate standard ammunition boxes or weapons, and there was also space for several soldiers with their gear. The landing gear featured light trusses with vertical uprights at the corners of the cargo area, each fitted with a wheel, with telescopic shock absorbers based on springs. In 1961, the development company constructed a full-size model of the XV-8 Fleep aircraft and subjected it to wind tunnel testing, during which no significant issues were encountered. This suggests a promising outlook for the project's development and potential deployment. The proposed appearance of the machine allowed to fly, and the combined control of changing the position of the wing and keel could give the desired maneuverability. According to the results of the tests in the wind tunnel, it was recommended to continue the work and begin a full test on the airfield. For use in testing, the first prototype was built with the serial number 6313003. It was built on the original project and fully consistent with the above description. The initial prototype of the Fleep, distinguished by its characteristic appearance, underwent successful runway runs without any issues. However, challenges emerged during attempts to lift the flying Jeep into the air, highlighting both its strengths and weaknesses. To achieve takeoff and landing, a runway length of 170 meters was required, demonstrating the effectiveness of the wing's optimal angle of attack. However, this design feature proved to be a drawback in other flight modes, as swinging the wing and adjusting its angle of attack didn't provide the necessary control. The lack of adequate control in flight could potentially lead to serious consequences, particularly considering the intended military application of the equipment. Consequently, the XV-8 project required significant improvements to address these shortcomings. Further analysis identified necessary enhancements, including simplifying the wing's angle of attack control system to allow fixation of the central tube in one of two positions. Additionally, the updated design necessitated the incorporation of a complete tail with a set of control surfaces to improve maneuverability. The revised project aimed to meet these new requirements while preserving the compactness and lightweight characteristics of the aircraft's structure. Consequently, a second prototype, identified by the factory number 6313004, was promptly constructed according to the updated specifications. In accordance with the updated requirements, the second machine Fleep FWAUV received a new version of the power elements of the wing. The three pipes were now connected by a transverse truss consisting of several separate elements. Instead of a complex structure mounted on the fuselage, a set of racks of a simplified design was used. At the same time, the hinge was kept to change the angle of attack of the wing. It was decided to streamline the design of the aircraft further by replacing the four-point chassis with a more simplified configuration, opting for a single central location for the front struts. Additionally, the traditional keel was eliminated, making room for more sophisticated components. The revised tail configuration featured two inclined planes, forming a V-shaped tail on the elongated tail section of the fuselage platform. These planes housed fixed components as well as pivotally mounted parts that could function as rudders. By synchronously or differentially deflecting these rudders, control over roll or yaw could be achieved. Another controlled surface, acting as the elevator, was positioned on the rear edge of the fuselage platform. In the updated Ryan XV-8 Fleep project, it was proposed to utilize changes in the wing's angle of attack solely during takeoff and landing. During horizontal flight, the wing would remain fixed in the appropriate position, with control primarily relying on the tail rudders. Prototype number 6313004 underwent testing, affirming the effectiveness of the modifications implemented. The handling significantly improved, reducing the risk of accidents. This advancement allowed for comprehensive flight tests to establish the machine's characteristics. The second prototype demonstrated a maximum flight speed of 96 km an hour, with a cruising speed slightly below 90 km an hour and a flight range of 193 km. With successful test results, the project's future prospects were determined, indicating promising potential for further development. A characteristic feature of the first version of the Project XV-8 FWAUV was the maximum possible simplicity of the design, which allowed good weight returns to be achieved. Noticeable refinements of the device necessary to increase manageability and reduce the likelihood of an accident led to some increase in its own weight and a corresponding decrease in other parameters. In conclusion, despite its initial promise, the Ryan XV-8 Fleep project didn't meet the expectations of the potential military customer due to shortcomings in controllability and performance. The first version lacked adequate controllability despite its advantages in size and cargo capacity, while the second version sacrificed certain parameters in favor of improved controllability. Recognizing the limitations of the existing design, further development of the XV-8 project was deemed impractical, leading to its closure. However, the flexible wing used in the project showed great promise and potential for various applications. Despite its simplicity, the Rogolo wing design proved to be of significant interest and paved the way for advancements in ultralight aviation. Although the XV-8 project didn't achieve tangible results in military re-equipment, it played a crucial role in advancing the understanding and development of flexible wing technology, contributing to future innovations in aviation.
As Britain and the Allies struggled for survival in a fierce battle with the Nazis, American industrial might was mobilized to supply them with the weapons and machines to beat back the German onslaught. Millionaire Howard Hughes was anxious to participate in the war effort to do his part to defeat Hitler. His intentions were not completely altruistic. A military contract would also have been extremely profitable. Hughes built the prototype D-2, a speedy wooden fighter/bomber entirely with his own money and in secret. He hoped to amaze the U.S. Army Air Force with it, but the plane was flatly rejected. Fortunately for Hughes, he had friends in high places. When President Roosevelt declared war on December 8, 1941, he had not only to consider the fate of the free world and the lives of millions of American soldiers, he also had to weigh the risks to his own sons. Elliott Roosevelt was a member of the U.S. Army Air Force. He had received his captain's commission on his 30th birthday in 1940. At the time, Roosevelt was battling for a third term in office, and there were cries of nepotism. But General Henry Hap Arnold, chief of the Air Corps, silenced those rumors. Elliott Roosevelt's poor eyesight left him classified as 4F, or unfit to fly, but he still managed to carve out a respectable career, participating in 89 combat missions. Reconnaissance was his specialty, and he was considered the leading expert in recon in the European theater and a pioneer in aerial night photography. While commanding the 3rd Reconnaissance Group in Operation Torch, the invasion of North Africa, Roosevelt had a chance to fly on board a speedy de Havilland Mosquito. He was so impressed with de Havilland's wooden wonder, he became a passionate advocate of British aircraft and believed American-made B-17s and P-38s were sitting ducks against the German defenses. His enthusiasm may have blinded him when a sly Howard Hughes presented him with a prototype for his own wooden aircraft, the D-2. The D-2 was a twin-boom fighter just like the Vultee Spruce Goose, designed by Hughes' former employee Richard Palmer. Palmer left Hughes for Vultee because he was tired of the company's lack of focus. The D-2 also had a remarkable resemblance to the P-38 Lightning. They were so similar, Hughes did not believe it was a coincidence, and he testified to the Senate that Lockheed had stolen his design. Though the D-2 had been rejected by the U.S. Army Air Force, when Colonel Elliott Roosevelt came to town looking for a new reconnaissance plane, Hughes dazzled him Hollywood-style to salvage a contract. The P-38 Lightning had been the workhorse reconnaissance plane for the U.S. Army Air Force, but by 1943, they were looking for an upgrade. Colonel Roosevelt, an expert in recon, was asked to explore what aircraft were in the works that might take over for the P-38. Hughes spared no expense when Roosevelt came to see his plant in Culver City, California. A line of limousines greeted the president's son and his staff at the airport, and they were taken on the trip of their lives. Women and starlets were thrown at them. They were treated to Hollywood's most extravagant parties in the hottest nightclubs. A married Roosevelt was introduced to his next wife, Faye Emerson, an up-and-coming actress with whom he would have a scandalous affair. In the midst of all this partying, there was time to see the D-2. Its Duramold body, a type of plywood bonded with plastic and molded under heat and pressure, would certainly have impressed Roosevelt, who was enamored with a Mosquito. By the time Colonel Roosevelt left California, he was sold on the D-2. He became an enthusiastic salesman for Hughes when he briefed General Arnold and his father on the project. Arnold was in a difficult position, as Material Command had already rejected the aircraft. They did not believe Hughes had the facilities or track record to deliver on an order. In the end, Arnold had no choice but to listen to the president's son. He ordered the XF-11, an all-metal and larger reconnaissance version of the D-2. The decision caused an uproar in the Army Air Force, not only because the D-2 had been rejected, but also because they already had a similar plane in development, the Lockheed Chain Lightning. The XP-58 was a long-range heavy fighter which could outperform the D-2, and it came from a known and reliable aircraft and manufacturer, the P-38 Lightning, built by Lockheed. Uproar or not, Elliott had his father's ear. Hughes won a $43 million contract to build 100 XF-11s, a contract that would be worth $500 million today. Unfortunately for the Army Air Force, their worst fears about Hughes came to be. Work progressed slowly on the XF-11. Each of its Pratt & Whitney 28-cylinder radial engines drove a pair of contra-rotating four-bladed controllable pitch propellers. It was hoped this style of prop would increase performance and stability, but the whole system was too complex and ultimately scrapped. As years passed, the XF-11 project, forced on the U.S. Army Air Force, became increasingly unpopular. The original D-2 prototype was mysteriously destroyed in a fire in November of 1944. At the time, Hughes and the U.S. Army Air Force were fighting over who should pay for the original development costs. With the prototype a pile of ash, the two sides agreed to split the costs. It was an accident which was highly convenient for the millionaire. Like the XF-11, controversy followed Colonel Roosevelt as the war progressed. Project Aphrodite was a joint mission between the U.S. Navy and U.S. Army Air Force to destroy heavily fortified German submarine pens and V-2 sites with bomber drones. The pilot and co-pilot would take aircraft heavily loaded with explosives to altitude before parachuting to safety. A mothership remotely controlled the bombers the rest of the way via radio. In later years, Elliott Roosevelt claimed to be in the Mosquito chase plane that recorded the tragic death of Lieutenant Joe Kennedy Jr., brother of future President John F. Kennedy. His plane inexplicably detonated before it reached its target. Elliott asserted that he actually flew through the deadly fireball that ensued, but there is no record of the president's son participating in the mission. There was also some controversy when Roosevelt was finally awarded his wings. General Arnold, who had been forced to accept Hughes XF-11, also had his arm twisted to intervene in Colonel Roosevelt's final promotion. In January of 1945, Arnold ordered General Carl Spaatz to appoint Elliott, whose poor vision had left him classified as 4F, or unfit to fly, as a rated pilot. The president then submitted his son's name to the Senate for promotion to brigadier general. On April 12, 1945, America mourned the death of President Roosevelt. He had accomplished much during his tenure, guiding them out of the Depression and through the war. As tragic as his passing was, it did untie the hands of General Arnold. He was finally able to put millionaire Howard Hughes in his place. The XF-11 order was canceled a month after the president's death on May 11, 1945, though Hughes was allowed to continue to work on the prototypes. By the time the war ended, Hughes still had little to show for all the money spent on the XF-11. It would be another year before a prototype would fly, and the first flight ended in a crash that nearly killed him. The XF-11 was not Hughes's only multi-million-dollar scandal. His behemoth transport, the H-4 Spruce Goose, was more of a lame duck and was yet to fly. With millions of dollars poured into both projects, questions swirled in the Senate about what Hughes was doing with the money. In 1947, the Brewster Committee looked into the spending irregularities surrounding these projects.
I put the sweat of my life into this thing. I have my reputation rolled up in it. And I have stated several times that if it's a failure, I'll probably leave this country and never come back. And I mean it.
Elliott Roosevelt and Johnny Myers were also called as witnesses. Myers, a publicist who worked for Hughes, gave a detailed expense report of all the perks Roosevelt had received during his time in California.
Well, now, can you tell me why you were charging up to aircraft production $132 for nylon hose for Miss Emerson?
Because she'd been very charming. Just like the presidents up higher. The girls were very pleasant.
What has that got to do with aircraft production?
They just went along. Every company in the business did it. We're no different.
Well, but is it... You say because she was very charming, that's the reason that you charged up $132.
That's right.
For the which would go into the production of airplanes.
That's right.
And now, will you tell us why you gave her $20 and charged it up to the company to go home if she was very charming?
What's you tapped me. Listen.
Myers had even paid for Roosevelt's wedding to Faye Emerson. In his defense, Roosevelt claimed that he first heard about the XF-11 after the Culver City visit in a briefing from Arnold.
And there are efforts to find out whether there was any connection that I might have had with the chief executive, which might have had an effect on any war contracts. And I'm here to give you the complete facts. It is undoubtedly true that he bought some tickets to, from New York to Washington. But I still want you to put the question to him, was he completely positive that one of those tickets was for Elliott Roosevelt?
Well, I'll put it right to him now. Mr. Myers, what do you say? Look at that sheet. You told us about them being lost and buying the fares back. Now, what do you say about it?
Just what it says here. It says Colonel Elliott Roosevelt Party.
Yeah.
So I didn't testify that he was one of them. He could have been one of the other fellas. Did I say that under the word Elliott Roosevelt Party? What?
During a break in hearings, Hughes decided to give the Senate all the evidence they needed that the Spruce Goose was fit to fly. While taxi testing the aircraft, he took the H-4 on its first and only flight. In daredevil fashion, Hughes proved to the cameras and reporters that the millions of American tax dollars had not been squandered or misappropriated. The millionaire used his Hollywood dazzle to save his own skin.
Over the years, scientists and designers across various nations have devoted efforts towards crafting aircraft with the most minimal takeoff and landing requirements. This approach aimed to reduce the demand for expansive landing sites, thereby enhancing operational versatility. However, achieving such benefits posed significant challenges, prompting aircraft manufacturers to seek unconventional technical solutions. Among the pioneering aircraft to successfully demonstrate shortened takeoff and landing capabilities was the Ryan VZ-3 Vertiplane. In the 1950s, American company Ryan Aeronautical embarked on the development of innovative aviation technologies aimed at improving these crucial flight characteristics. Leveraging a combination of established and novel technical solutions, the company aimed to produce an experimental aircraft meeting the desired specifications. The underlying technologies of this pilot project held promise for potential application in the creation of practical aircraft in the future. First of all, such a technique could interest the Army. To reduce the takeoff distance or to ensure vertical ascent into the air, different methods and designs of the aircraft can be used. In their new project, the designers at Ryan decided to apply the technology of deflecting the airflow. The wing of the aircraft of the new model was to be equipped with developed flaps of a large size that could have a significant impact on the movement of air, changing its direction and creating additional thrust. To test the original proposal in practice needed the help of a specialized experimental aircraft. The new project was assigned the working corporate designation Ryan Model 92. Following the expressed interest of the US Army in its development, a new designation emerged, VZ-3, along with the fitting name Vertiplane. Over time, the military designation of the project was further supplemented with new letters, VZ-3RY, under which it gained widespread recognition. The objective of the VT-plane project was to construct an experimental aircraft capable of vertical or shortened takeoff and landing. It aimed to practically test original concepts that could significantly simplify the design. The experimental aircraft wasn't intended for payload carriage or weaponization, hence eliminating the necessity for high load capacity or specialized equipment. Only elements directly pertinent to the project's primary objectives were to exhibit comparative complexity. The proposed design for the VZ-3 aircraft entailed a high wing configuration with two propellers mounted on underwing gondolas and a fixed landing gear. Its fuselage featured a large teardrop-shaped elongation. Notably, the nose and central sections of the fuselage, distinguished by an enlarged cross-section, boasted vertical sides and a horizontal bottom, seamlessly integrated with other surface areas. Additionally, the tail boom sported a tapering truncated cone shape. In the central part of the fuselage, flush with its upper surface, the wing of the original structure was attached. On the tail, it was planned to install a T-shaped tail unit with a small keel sweep and a rectangular stabilizer. The nose of the fuselage accommodated the cockpit for a single pilot. In the first version of the project, the pilot was to enter through a large opening between the roof and the sides of the fuselage. Even in the initial stages of the project, it became apparent that the cabin glazing design would not offer the necessary visibility during takeoff and landing. Consequently, an additional window with glazing was incorporated into the bottom of the nose fairing, enabling the pilot to maintain visual contact with the runway. The primary innovation of the Ryan VZ-3 project lay in its unconventional wing design, featuring elaborate mechanization directly influencing the aircraft's key characteristics. The proposal involved installing a rectangular-shaped high-placed wing in the central part of the fuselage. Despite its relatively modest elongation, other design features compensated effectively for this limitation. Notably, the wing boasted a substantial profile thickness. Two small-sized gondolas housing gearboxes and propeller shafts were positioned beneath the wing. These gondolas featured large trapezoid-shaped combs aimed at mitigating airflow overflow and preventing it from exceeding prescribed limits. The experimental aircraft's wing featured sizable retractable flaps, comparable in area to the wing itself. To enhance takeoff and landing performance, these flaps could extend from the wing and tilt backwards, assuming a position close to vertical. Additionally, the wing, flaps and tip ridges formed a box-shaped system designed to significantly influence aerodynamics and effectively redistribute airflow. It was due to the redistribution of the flow and the direction of the air downwards that was supposed to get a shortened or even vertical takeoff. The experimental aircraft received an unusual power plant equipped with two propellers. The Avco Lycoming T53L1 turboshaft helicopter engine with a power output of 1,000 horsepower was situated in the rear fuselage. Air intake was facilitated through a bottom-mounted intake device and an internal channel of minimal length, while fuel was sourced from built-in tanks. A shaft positioned in front of the engine transmitted power to the central gearbox, which in turn distributed torque to two shafts running parallel to the wing spars. Subsequently, power was transferred to the propellers through a series of gears. Three-bladed propellers were affixed to the shafts emerging from the underwing gondolas, allowing for the gondolas to maintain a minimal size. Their width remained consistent with the pylons on which they were mounted, thereby minimizing obstruction of the plane's surface area. Each propeller boasted a diameter of 2.79 meters, effectively covering nearly the entire frontal projection area of the wing, thereby positively influencing flight performance. The experimental aircraft of this new model was designed to exhibit acceptable controllability across all flight modes. To achieve this, it was equipped with both traditional control surfaces and non-standard mechanisms serving similar purposes. Pitch and yaw control during speed flight modes were intended to be managed by the elevator and rudder respectively, situated on the stabilizer and keel. At low speeds, such devices sharply lost their efficiency, which, in addition to them, there was developed a system of gas rudders connected to the engine. The plane couldn't be completed with ailerons for this reason. The roll control was proposed to be carried out by changing the operating parameters of the two propellers. An increase in the thrust of one of the screws caused the corresponding plane to rise upwards under the action of the increased lift force and thus led to a change in roll. The initial version of the Ryan VZ-3 Vertiplane project featured a three-point chassis with a tailwheel. The primary supports of this chassis comprised three tubes of varying lengths, with wheels situated beneath the central fuselage section. A tail skid was positioned at the rear. Due to the aircraft's aim for minimal takeoff weight, provisions for retracting the chassis were not included. The dimensions of the first version of the aircraft were as follows: length 8.3 meters, wingspan 7.14 meters, height 3.25 meters. The normal takeoff weight was set at 1,180 kilograms, with the aircraft designed to be operated by a single pilot located in the forward cabin. The restricted takeoff weight constrained fuel capacity, with high speed and extended range not being primary project objectives. Instead, the focus was on achieving favorable takeoff and landing characteristics. The pilot project was completed in 1957, and by early the following year, the first prototype underwent testing. On February the 7th, it was transported to the airport for ground tests, which preceded its inaugural flight. Prior to this flight, extensive ground testing and wind tunnel trials were conducted over the course of nearly a year. The efforts yielded valuable insights into the aircraft's behavior across various modes of operation and identified areas for necessary improvements. According to the results of ground tests, an experienced aircraft was allowed to fly. The first flight of the experienced Vertiplane took place on January 21, 1959. The use of large flaps, together with the wing forming a box-like structure, gave certain results. In practice, it revealed the possibility of a sharp reduction in takeoff and run. At the same time, it wasn't without its problems. The initial challenges with the 1,000 horsepower engine became apparent early on, as it failed to generate the necessary thrust to take off without a sufficient headwind, resulting in extended run-up requirements. Furthermore, occasional handling issues arose under certain conditions. The primary focus of the test flights was to ascertain the actual performance characteristics during takeoff and landing modes. Evaluation of the aircraft's behavior in horizontal flight was of secondary importance. Testing revealed that the current configuration still couldn't execute vertical takeoff. Nevertheless, it showed promising potential for reducing run-up and runway requirements, albeit often reliant on favorable headwinds. Throughout the first months of 1959, Ryan Aeronautical and US Army specialists managed only about 24 relatively successful test flights. Unfortunately, during the 21st flight, the experimental VZ-3 experienced a mishap resulting in damage. Despite this setback, the decision was made to restore the aircraft and continue testing. However, shortly after the accident and the commencement of repairs, the US military lost interest in the unconventional project and withdrew its participation. This decision was influenced by various factors, leading to a halt in further collaboration on the project. However, the aircraft was still needed by science, because of which, after repair, the prototype was transferred to NASA. Further work was carried out by the Aerospace Agency specialists. The tests were resumed in February 1960, but soon stopped again. During the next descent into the air, there were problems that forced the pilot to leave the car. Fortunately, the aircraft sustained minimal damage and was deemed repairable. This presented an opportunity to implement several new solutions inspired by the breakdowns and subsequent repairs. The prototype wasn't merely restored, it was also reimagined according to an updated project plan. These enhancements were informed by ground and aerodynamic tests, as well as insights gained from the initial test flights. Foremost among the changes was a significant overhaul of the chassis. The design of the main landing gear underwent modifications, and the tail skid was replaced with a fixed nose strut. This adjustment altered the aircraft's stance on the ground and during takeoff runs, requiring it to rest level with a slight nose-down attitude. Refinements to the chassis, aimed at enhancing visibility during takeoff and landing, prompted the removal of glazing from the nose fairing. Furthermore, the cabin underwent a transformation, shedding its existing glazing and roof. Now, only a small visor remained to shield the pilot, with no additional elements of the canopy present. Additionally, a portion of the metal fuselage skin in the nose section was replaced with linen material. Measures were taken to change the aerodynamics of the aircraft. In place of the crutch under the fuselage, an additional comb appeared, which improved the stability along the course. To improve the characteristics of the wing, deviated slats appeared on the plane. Also changed were the size of the flaps. Various modifications were implemented to simplify or enhance specific elements of the aircraft and improve its aerodynamic performance. By the end of 1960, NASA experts once again brought the experienced Ryan Vertiplane to the runway. Inspections of the aircraft continued until 1961, primarily focusing on studying its takeoff and landing characteristics with different wing configurations, controllability in various modes, and other factors. Horizontal flight characteristics were also evaluated multiple times throughout the testing process. Over several stages of testing, interspersed with repairs, a wealth of diverse information was gathered. The prototype VZ-3 was subjected to testing at speeds ranging from 6 knots, 11.1 km an hour, to 80 knots, 148.1 km an hour, and demonstrated acceptable performance across this spectrum. Optimal takeoff and landing parameters were achieved within the 20 to 25 knot range, 37 to 46 km an hour. For instance, at speeds of approximately 35 km an hour, the aircraft required 9 to 10 meters of runway, slightly more than its own length, to take off. Maintaining lift at this speed allowed the aircraft to ascend to an altitude of 1.1 kilometers. Early in the testing phase, pilots encountered the phenomenon known as ground effect. At altitudes below 5 meters, air currents reflecting off the ground began to adversely affect the operation of the propellers and wing, reducing their efficiency. Additionally, aircraft stability diminished, potentially resulting in an uncontrolled dive and subsequent crash. Incorrect use of gas rudders exacerbated these risks during such conditions. The negative impact of the underlying surface particularly hampered the implementation of the landing. Nevertheless, recommendations were soon formed on the optimal modes of descent and touching the ground. To avoid loss of control and fall, the pilot on landing, dropping below 15 feet 5 meters, had to withstand speeds of around 20 knots. Maintaining a descent angle of several degrees was crucial during landing. Experimental trials pushed the landing speed to 40 knots, 74 km an hour, and the descent angle to 16 degrees, but such landing modes posed significant risks. From the initial wind tunnel tests, it was evident that the Ryan VZ-3 Vertiplane, despite its name, would not be capable of vertical takeoff and landing, a conclusion confirmed during full flight tests. Nevertheless, the project's creators achieved a substantial reduction in runway length, aligning with the original project objectives. Testing of the prototype, revamped according to the updated project specifications, persisted until 1961. Following their conclusion, American experts meticulously analyzed the amassed data, producing numerous reports and scientific works. This comprehensive study spanned several years, shedding light on various aspects of the aircraft's performance. By this time, the prototype had been relegated to storage, with little hope of resuming flights. Indeed, after 1961, the experienced VZ-3 never took to the skies again. After all of the required research and scientific work was completed, the car was decommissioned as superfluous. Unlike some other unique examples of aviation technology, the only VT plane was not dismantled for metal. The aircraft was handed over to the Army Aviation Museum, Fort Rucker, Alabama, where it remains to this day. It's worth noting that the prototype Ryan Model 92 VZ-3 Vertiplane wasn't the sole platform dedicated to testing and refining innovative concepts aimed at enhancing aircraft takeoff and landing capabilities. Throughout the 1950s, numerous similar-purpose aircraft were developed and tested by several other US aircraft manufacturers. Like the VZ-3, these aircraft merit separate examination and review for their contributions to advancing aviation technology in this regard.
In the waning days of World War II, the world of military aviation was at a turning point. By the close of 1944, America's prop-driven B-29 Superfortress was pushing the limits of extended-duration bombing missions thanks to technological advances like its uniquely pressurized cabin and remote-controlled defensive turrets. On the other side of the fight, the Nazi Messerschmitt Ne-262, the world's first operational jet aircraft, was proving that the days of propeller-driven fighters were numbered. In a very real way, the future of warfare in the skies was so in flux that in the minds of many, just about anything seemed possible. At the onset of World War II, a number of British Royal Air Force units were still operating biplanes. By the end of the war, jet fighters were screaming across the sky in massive air battles for the future of Europe. The famed Supermarine Spitfire, so often credited with winning the Battle of Britain, offered its pilots little more than a floating reticle on the windscreen, and 15 seconds worth of ammunition if a pilot were so bold as to release it all in just one volley. As technology advanced, many aircraft were fitted with more powerful guns and more efficient engines. But dogfighting remained a close-quarters shootout, a far cry from the over-the-horizon missile engagements of today. The race for being the most technologically innovative country was more important than ever, particularly in aviation, as entirely new air forces were built from the ground up. Almost 1 million aircraft were produced worldwide for warfare, and even though the United States joined the war later than most of the other technologically advanced countries, they didn't want to be left behind to keep up with the new technologies such as jet power and flying wings. But it was that powerful belief that air warfare was changing that prompted a number of governments to pursue unique and original air combat ideas that, in hindsight, seemed downright crazy. One such program was Northrop's XP-79, better known as the Flying Ram or the Flying Chainsaw. They wanted to design something that had never been seen before. The XP-79 was at a time thought to be the answer. Its purpose was to attack enemy bombers at unusually high speeds by ramming into them without suffering any damage itself. Its unique shape and strong magnesium-covered armor would allow it to slice off the tails and wing from any enemy aircraft. The crucial battle for air superiority during World War II saw the secret development of many aviation technologies, but it would ultimately be brute bombing force that would pound Germany into submission. In the late stages of World War II, just as the odds were starting to favor the Allied forces, American bomber formations in Europe were frequently attacked by a new German rocket-powered jet, the Messerschmitt Me-163 Comet. And even though these small jets brought plenty of show and theatrics to aerial combat, they weren't very effective. Still, the American public marveled at the design and technology of these innovations and wondered when they would get a small fighter jet of their own. What they didn't know was that the U.S. Army Air Forces were already working with Northrop Corporation on a project of just that magnitude. The Northrop XP-79 was the brainchild of this ambitious project. Jack Northrop, who is one of America's most innovative aircraft designers, intended for it to ram into enemy bombers and split them open. The XP-79 was much smaller than its stealthy successors would be, with a fuselage built only large enough for a single pilot to lay down in horizontally, making this aircraft's first significant departure from common flying wing designs as we know them today. Northrop and his team believed that the pilots would be able to withstand greater G-forces if they were oriented in a laying position, and because the XP-79 was designed to utilize jet propulsion, the shift seemed prudent. Born in Newark, New Jersey in 1895, Northrop grew up in Santa Barbara, California. In 1916, Northrop's first job in aviation was working as a draftsman for the Santa Barbara-based Lockheed Aircraft Manufacturing Company. After the outbreak of the First World War, Northrop was drafted into the U.S. Army, where he served in the Army Signal Corps. Northrop served in the military for 6 months before Lockheed successfully petitioned for his return to work in the private sector. In 1923, Northrop joined Douglas Aircraft Company, participating in the design of the Douglas round-the-world cruiser and working up to project engineer. In 1927, he rejoined the Lockheed brothers in their newly founded Lockheed Aircraft Company, working as chief engineer on the Lockheed Vega, the civilian transport monoplane with a cantilever wing that produced unusually high performance for that period, and was also widely used by such pilots as Wiley Post, Amelia Earhart, and Hubert Wilkins. In 1929, he produced an all-metal monoplane with pilot and engine within the wing structure. Although this aircraft had booms to attach to the tail group, it was in fact the step towards the flying wing. In 1929, Northrop struck out on his own, founding the Avion Corporation, which he was forced to sell to the United Aircraft and Transport Corporation in 1930. In 1932, Northrop, backed by Donald Douglas of Douglas Aircraft, founded another company, the Northrop Corporation, in El Segundo, California. There, he worked as chief engineer, and he helped design the A-17 attack plane for the Air Corps as well as the BT-1 bomber for the Navy during the Great Depression. This company built two highly successful monoplanes, the Northrop Gamma and the Northrop Delta. By 1939, the Northrop Corporation had become a subsidiary of Douglas Aircraft, so Northrop founded another completely independent company of the same name in Hawthorne, California, a site located by Moy Stevens, one of the co-founders. While working at this company, Northrop focused on the flying wing design, which he was convinced was the next major step in aircraft design. His first project, a reduced-scale version tested in 1940, ultimately became the giant Northrop YB-35. The Northrop XP-56 Black Bullet, a welded magnesium fighter, was one of the more significant of his World War II designs, along with the Northrop P-61 Black Widow, the first American night interceptor, of which more than 700 were constructed. His inventions continued into the post-war era of jet aircraft to produce the Northrop F-89 Scorpion all-weather interceptor, the Northrop YB-49 long-range bomber, the Northrop Snark intercontinental missile, and automatic celestial navigation systems. He produced a number of flying wings, including the Northrop N-1M, Northrop N-9M, and Northrop YB-35. His ideas regarding flying wing technology were years ahead of the computer and electronic advances of the fly-by-wire stability systems, which allow inherently unstable aircraft like the B-2 Spirit flying wing to be flown like a conventional aircraft. The flying wing in the pursuit of low-drag, high-lift designs were Northrop's passion and its failure to be selected as the next-generation bomber platform after World War II, and the subsequent dismantling of all the prototypes and incomplete YB-49s were a severe blow to him. He believed that such a jet with a single airfoil surface would have the most effective lifting capabilities. The lack of a fuselage and tail unit would mean less drag to affect overall performance and lower production costs. In his mind, it was a win-win. In 1942, Jack Northrop proved himself to be well ahead of his fellow American competitors and previous employers when his flying wing concept took a dramatic step forward. He convinced the United States Army Air Forces that he could build a flying wing fighter jet that could fly faster than the speed of sound. In January 1943, a contract for two prototypes with designation XP-79 was issued by the United States Army Air Force. Northrop's program began in 1943 with the code name Project 12 as its aircraft designation. It would have to be developed with the utmost secrecy as spying eyes could steal the advanced technology. Their plan was a rocket-powered flying wing designed with a total wingspan of only 32 feet. It would also be less likely to be spotted by enemy radars. Such a flight mission was not by the faint of heart. Experts believe that since the fighter's layout was so revolutionary and new, test bladder prototypes had to be built to verify the validity of the concept. Given the Northrop designation NS-12, the gliders were also given project numbers from the USAAF. Confusingly, two project numbers were used, one MX-324 when discussing secret aspects of the power gliders, and another MX-334 relating to the aircraft being built and flown as pure gliders. The NX-334 emerged as a flying wing glider with no tail surfaces, similar in layout and construction to the Northrop N-9M. Completed in late spring 1943, the number 1 MX-334 was tested in NACA Langley's wind tunnel, after which a large wire-braced fin was added to ensure directional stability at high speeds. For a more comprehensive test, a Lockheed P-38 Lightning was used to tow the aircraft on its first proper flight on the 2nd of October 1943. It had a tricycle undercarriage, which ensured a level floor when the aircraft was at rest. The power plants were designed to be placed deep into the fuselage aft. The development of the Aerojet's rocket motor lagged behind. In an effort to get in step with the program, that is, to meet its contract obligations and actually get a rocket-powered aircraft into the air, Aerojet built a smaller interim 200-pound rocket motor, the XCAL 200, fueled by monoethyl aniline and nitric acid. The rocket fuel burned quickly, and a flight time of just under 4 minutes was estimated, although the performance wouldn't be enough for a production model. The installation of this motor meant that the glider number would only now serve as a powered air vehicle for the P-79 program under the MX-324 program. Following the crash and complete destruction of the glider, the number 2 glider stepped up to become the powered MX-324. Testing with the rocket motor commenced on the 22nd of June 1944, with the first air tow launch for a powered flight on the 5th of July 1944, making it one of the first US-built rocket-powered aircraft to fly. Adjacent to the NX-324's development was the Northrop XP-79. This model was of greater military value, as it was designed to compete with the German Messerschmitt Me-163 Comet. Originally, just as with the MX-324, it was to be rocket-powered, and it also required a pilot lying prone in the cockpit. The XP-79 was to be able to reach speeds of 500 miles an hour, and the cabin would be pressurized to ensure the survival in the estimated 40,000 feet ceilings. In contrast with the authentic flying wings, the XP-79 design had a large swept wing surface paired with vertical tail fins at the rear for extra stabilization and maneuverability. Aerojet was never able to overcome the limitations of the XCAL 200 rocket tested with the MX-324. Instead, Westinghouse was chosen to deliver a pair of new turbojet engines. Each of these 19 Bs would generate 1,150 pounds of thrust. The cockpit was at the center of the triangle's apex and straddled on either side by twin intakes to aspirate the twin engines. The undercarriage had 4 landing gear legs and 1/4 arrangement instead of the more conventional 3-legged form. The armed forces' most fundamental requirement for this project was that the new flying wing would be able to ram into enemy bombers. The Germans had aircraft utilizing similar concept already in battle. Even though these yielded mixed results, America wanted the tactic in their arsenal as well. It was an approach that, by modern standards, now sounds delusional. After the testing period finished, the XP-79 was supposed to fly out from nearby Allied air bases against incoming enemy bombers. In practice, the XP-79 would launch from nearby Allied air bases against a flight of incoming enemy bombers. It would have launched quickly through the use of rocket boosters and reach high altitudes within minutes. With no armament intended for the design, the XP-79 pilot was expected to make several high-speed passes through enemy formation and utilize the reinforced wing leading edges to effectively slice through the airframes of enemy bombers themselves. As the XP-79 would have moved at such high speeds, enemy gunners could theoretically not target and fire upon the aircraft within time, so very little danger was apparent to the XP-79 pilot, aside from the fact that he was expected to ram his exceptional aircraft into the enemy. An armored glass mounting at the cockpit would protect the pilot's head and face during dives, while the body would be covered in heavy-gauge magnesium armor plating to mitigate the damage while ramming into enemy aircraft. However, by 1945, the XP-79 was being readied for a kind of battle that no longer existed. Fear of Hitler's bombers reached their greatest heights in the Battle of Britain, but further Luftwaffe bombing formations never materialized into the mid-late war years. As the prospect of facing off against wave after wave of German bombers subsided, the XP-79 mission profile became a moot point. Among the US AAF brass, someone must have recognized the absurdity of that idea, because the XP-79B order also stipulated that the fighters should accommodate 450 caliber Browning machine guns outboard of the jet engines. Neither the guns nor the cockpit pressurization system were destined to be installed in the plane. The airframe used to create the XP-79B was formerly the No. 3 XP-79. since it could be more easily converted into a turbojet-powered air vehicle rather than a rocket-powered air vehicle. The first flyable XP-79B was painted white and was given the serial number 43-352437. It was struck to the Muroc Dry Lake testing facility in preparation for its first flight. Its first ominous taxiing tests were conducted in June 1945, during which all of the tires burst on at least several occasions. The flying chainsaw later actually had only one flight test, which lasted less than half an hour and ended with disastrous consequences. Northrop chose test pilot Harry Cosby for the flight test. On the morning of September 12, 1945, Crosby taxied out and lined up for takeoff. He powered up the plane's two Westinghouse Electric Corporation Model 19B engines to begin his takeoff roll and, at about 120 miles an hour, rotated the nose landing gear wheel and lifted off from the dry lake bed. At first, the unique semi-flying wing piloted by Harry H. Crosby performed well. Then, about 15 minutes into the test, the twin turbojet-powered XP-79B went completely out of control. The craft entered a steep vertical spin and crashed on the ground, where it burned completely, fueled by the highly flammable magnesium metal of its body. At the first sign of trouble, Crosby, who had been piloting from a prone position, struggled to escape. He managed to remove the escape hatch above his head, but the 38-year-old Crosby, most likely knocked unconscious by the wildly gyrating air vehicle, was bucked out of the cockpit. He fell to his death with his parachute still packed. After the crash, Northrop's founder and president issued the following statement. The takeoff for this flight was normal, and for 15 minutes, the airplane was flown in a beautiful demonstration. The pilot mounted confidence by executing more and more maneuvers of a type that would not be expected unless he were thoroughly satisfied with the behavior of the airplane. After about 15 minutes of flying, the airplane entered what appeared to be a normal slow roll, from which it did not recover. As the rotation about the longitudinal axis continued, the nose gradually dropped, and at a time of the impact, the airplane appeared to be in a steep vertical spin. The pilot endeavored to leave the ship, but the speed was so high that he was unable to clear it successfully. Unfortunately, there was insufficient evidence to determine the cause of the disaster. However, in view of his prone position, a powerful electronically controlled trim tab had been installed in the lateral controls to relieve the pilot of excessive Gs. It is believed that the deliberate slow roll may have been attempted, and that during this maneuver something failed in the lateral controls in such a way that the pilot was overpowered by the electrical trim mechanism. The USAAF accepted the number 1 XP-79B on a crash delivery basis in December 1945, and action was taken in January 1946 to terminate the remaining phases of the P-79 program, which had been an extremely advanced program for the era. The remaining unpowered MX-334, Blighter 1, did not survive, and its final disposition remains unclear. The Northrop Aircraft Corporation XP-79 program led to the first piloted flight of a rocket-powered aircraft in America. The XP-79B was unique in its semi-flying wing design and prone position of its pilot, as well as the floor-point landing gear arrangement, twin vertical tails, and Delos-type flight control system attached to either tip of its wing. In addition, its body was constructed from magnesium alloy rather than aluminum alloy. Unfortunately, America's first rocket man, Harry H. Crosby, was lost during the XP-79B's first and only flight. With his tragic loss and the demise of the XP-79B, no replacement was ordered. Northrop and his engineers determined the XP-79 control problem could be fixed for the next test. Still, the U.S. Air Force didn't want to risk any further disasters, so they decided to abandon the project. World War II was over anyways, and more conventional jet designs were already entering production. The techniques used to create the XP-79, however, aided in the development of other future projects. Northrop's obsession with flying wing designs finally came true when he developed his B-35 and B-49 bombers.
Even in an era where aircraft designers experimented with every conceivable shape and size, the prototype designed by Italian engineer Luigi Stipa and built by the Caproni Company in 1932 in place of a conventional fuselage, the airplane, known as the Caproni Stipa, consisted of a short, wide, hollow tube through which the propeller wash was directed. The inventive airframe designed by Italian aeronautical engineer Luigi Stipa and manufactured by the Caproni Company was in many ways like a cartoon aircraft, but it was functional. Today, some consider the Stipa the ugliest airplane ever built. Others simply regard it as an aerodynamic freak, a sort of man-made bumblebee. There are others, however, who see in this bizarre Italian contraption the direct predecessor of the turbofan engines used on today's commercial and military jets. Despite looking for a cartoon airplane, the Stipa Caproni could fly, and was briefly studied by NASA. The company was founded during 1908 by the Italian aviation pioneer and aeronautical engineer Giovanni Battista Gianni Caproni. Its principal manufacturing facilities were based in Taliedo, a peripheral district of Milan, close to Linate Airport, while the firm's Caproni Vizzola division was based in Vizzola Ticino, close to Milan Malpensa Airport. The firm initially produced a series of small single-engine aircraft, including the Caproni CA-1, CA-6, and CA-12. These became important milestones in the early development of Italian aviation. As such, Caproni became one of the most important Allied aircraft manufacturers during the First World War, being responsible for the design and manufacture of a large, multi-engine long-range bombers such as the three-engine Caproni CA-32, CA-33, CA-36, and CA-40. Caproni's bombers were a significant contribution in the development of heavy aircraft. The interwar period was a busy one for Caproni. While the end of the First World War had led to a rapid decrease in demand for bombers, impacting orders for much of Caproni's traditional product line, Caproni elected to redirect the bulk of the company's resources towards growing the civil aviation market. By the 1930s, the company's main subdivisions comprised Caproni Bergamasca, Caproni Vizzola, Reggiane, and the engine manufacturer Isotta Fraschini. Caproni's aircraft activity largely orientated towards the production of bombers and light transport aircraft. Perhaps the most distinctive of Caproni's aircraft was the Caproni CA-60 Transaereo, an experimental large flying boat designed for the civil sector. At the time, the concept of a large multi-engine flying boat to serve long-distance passenger routes was considered to be radical. During 1919, Caproni filed patents to his work on the concept. His large seaplane design, designated Caproni CA-60, was highly unorthodox, featuring 8 engines and 3 sets of triple wings. On the 12th of February, or 2nd of March 1921, the aircraft took off for the first time, proving to be both stable and maneuverable during its first brief flight, in spite of persisting tendency to climb. However, on March 4th, the sole completed aircraft was lost while attempting its second flight. Caproni continued to maintain its interest in innovative aircraft. One such example was the Stipa Caproni, also known as the Caproni Stipa, which was designed by Luigi Stipa and built by Caproni. Born in 1900, Luigi Stipa interrupted his education to serve in the Italian Army's Bersaglieri Corps during World War I. He later earned degrees in civil, hydraulic, and aeronautical engineering. Working for the Air Ministry, Stipa eventually became General Inspector of the Air Force Engineering Division. Stipa began to formulate a new theory on how to make aircraft more efficient. As a hydraulic engineer, he knew that the velocity of a fluid increased as the diameter of the tube through which it passed narrowed. Called Bernoulli's principle, the relationship between the velocity and the pipe diameter was a well-understood axiom of fluid dynamics by the 1920s. Applying Bernoulli's principle to airflow, Stipa believed he could increase the efficiency of an aircraft's engine by directing the prop wash through a Venturi tube. Stipa called this concept in-tubed propeller. After years of crunching numbers and testing models in a wind tunnel, Stipa thought he arrived at the optimum shapes for the prop and tube, as well as the ideal propeller RPM and proximity between the prop and leading edge of the tube. As it turned out, the optimum shape for the tube's inner surface proved to be almost exactly the same as that of an airfoil. Stipa published his findings at the Rivista Aeronautica, along with his design for a small single-engine testbed aircraft. He then petitioned the Air Ministry to have the prototype built and flown. Despite the radical nature of Stipa's design, at the time, the fascist government was actively encouraging technological development, particularly in aviation, to showcase Italian achievement. Now, it was just a matter of finding the right company to build such a rare aircraft. In 1932, the Air Ministry contacted the Caproni Aviation Corporation to construct the prototype. Clearly, no one in Italy was more qualified than Caproni to build Luigi Stipa's radical new prototype. The design consisted of a short, fat, tubular shape, open at the front and back, but narrowed in the middle, so that the air was compressed and pushed inward by the propeller. Notably, the tube was basically the fuselage, giving the aircraft a comic appearance. Moreover, the elliptical-shaped set of wings looked small, matted to the tube, and they required spears passing through the tube at the engine nacelle in the center. In addition, the cockpit housed a pair of tandem seats in a hump on top of the tubular fuselage. However, the line of sight was less than ideal, with the humped surfaces at the front and rear hampering the view, significantly restricting the landing and takeoff. Its power plant, a single 120-horsepower de Havilland Gypsy 3, was mounted in a nacelle suspended inside the center of the tube, with the prop located at the tube's leading edge. Furthermore, the aircraft required relatively low landing gear since the propeller was about the same diameter as the fuselage. An elliptical-shaped set of wings was mounted at the mid-position on the fuselage, with the main spars passing through the tube and the engine nacelle. Finally, a small rudder and elevators were attached to the tube's trailing edge directly in the slipstream. Capping off the plane's outlandish appearance was its light blue and cream color scheme, similar to ones used on racing planes of the day. Constructed mainly of wood, the Caproni Stipa was an oddly proportioned aircraft that has sometimes been compared with the GB's racers. It had a wingspan of 46 feet 10 inches and was 9 feet and 10 inches high, but it was only 19 feet 3 inches long. Its takeoff weight was 1,764 pounds, and it had a top speed of 81 miles an hour. When Caproni test pilot Domenico Antonini first flew the aircraft in October of 1932, the Caproni Stipa was a startling sight. As a result, the Stipa demonstrated a better rate of climb than conventional aircraft with similar power and wing loading, as well as a very slow landing speed of 42 miles an hour. In fact, the test flights confirmed that the intubated propeller increased engine efficiency, and the interior airfoil shape contributed to the lifting. It also proved to be notably quieter than similarly powered conventional aircraft. Ultimately, the Bumblebee proved superior to any other aircraft with similar engine ratings. Stipa's design not only had a faster rate of climb, but was extremely stable in flight, perhaps too stable, as some pilots found it difficult to change course. Still, the aircraft's docile handling was widely praised. But evidence indicates the rudder and elevators had to be enlarged, suggesting the designer overestimated their degree of effectiveness. The biggest drawback to Stipa's in-tube propeller was that it produced a great deal of aerodynamic drag. And, for a reasonably sized single-engine aircraft, the drag absolutely negated the configuration's benefits. Nevertheless, the Stipa Caproni was always meant to be a testbed and proved successful at that. In fact, its creator intended to use the design to produce larger, multi-engined aerial vehicles, even sketching numerous blueprints. He produced a number of such designs, some mixed with as many as 6 engines, none of which was ever built. After the initial testing, the prototype was delivered to the Air Force, which continued with its own test program. The results were of great academic interest, even drawing the attention of the National Advisory Committee for Aeronautics, or NACA, which closely studied the concept. However, no further development was undertaken. Encouraged by the interest in this project from the Italian government and the aeronautics community, Stipa presented his design not only to his country, but also to the United States and Germany. Ultimately, however, the strange construction did not offer any real advantages over its contemporaries and was soon abandoned. However, even though the Air Ministry did not embrace the inventor's theories, the Italians still publicized them as propaganda, and his work was published in many countries, including France and the United Kingdom. The French were interested enough to commission the development of a night bomber with in-tube propellers based on Stipa's design. Produced by ANF Muriot, the BN-4 night bomber would have carried a crew of 4 and been equipped with a retractable landing gear and 2 power-operated gun turrets. The plane was to have a wingspan of 59 feet, a top speed of 233 miles an hour, a range of 1,242 miles, and a ceiling of 33,000 feet. The nationalization and reorganization of France's aircraft industry in 1936 killed the project before a prototype was built. Stipa later claimed the Germans stole his patented ideas when they developed their V-1 flying bomb, although the pulse jet engine actually bears little relationship to his in-tubed propeller. The mysterious Heinkel T fighter design of 1940, however, bears a strong resemblance to some of Stipa's designs. Although little is known about the Heinkel T beyond a few drawings, it is said to have been designed for an engine developed by Victor Schauberger, the Austrian crackpot inventor regarded as the originator of the flying saucer. In 1934, German engineer Ludwig Koch presented a design for a deducted fan that used principles similar to those developed by Stipa, known as the Koch nozzle. This deducted fan system is still in use today. No further efforts were made to develop Stipa's intubated propeller, but in 1940, the Italians flew a more advanced derivative, the Caproni Campini N1. The new aircraft used a conventional radial engine to power a variable pitch deducted fan compressor inside the fuselage. The system required additional fuel in the compressed air, which burned in a combustion chamber in the tail. While the N1 was never practical, it did give the Italians the right to brag about having flown the first aircraft with an afterburner. Flight tests with the first prototype revealed several issues with the engine. It did not produce sufficient thrust to achieve the anticipated performance if it was matched to a strengthened airframe to withstand the high loading pressures. The engine generated considerable heat, which forced the pilot to fly with the canopy open throughout the flight, which, although effectively venting the heat, increased drag. According to aviation author Sterling Michael Pavlik, the N1 was heavy and underpowered, and conventionally powered Caproni Vizzola F4 was faster, which he attributed to limited national resources which left development programs underfunded. The surviving example is now on display at the Italian Air Force Museum at Vigna di Valle, near Rome, while the ground testbed, consisting of only the fuselage, is on display at the National Museum of Science and Technology in Milan. Then, after the end of World War II, Stipa was convinced that the jet engine was derived from his designs, and several historians also acknowledge the similarities between the tube propeller and turbofan engines, vindicating the Italian inventor and his creation to an extent. Luigi Stipa died in 1992, embittered at not being recognized as the true inventor of the jet engine. The story of Caproni Stipa would have ended long ago were it not for the efforts of Lynette Zuccoli and the Aerotech Queensland in Australia. They built it in 1998 and, in October 2001, succeeded with making 2 directional test flights with it, with Bryce Wolfe at the controls. Each flight covered about 660 yards and reached an altitude of approximately 20 feet, with Wolfe reporting that the replica was very sustainable in flight and performed much as the Italian test pilots reported that the original aircraft had 69 years to the month earlier. The aircraft was flown at least twice before being retired into static display, and it can be visited at Toowoomba City Aerodrome in Australia. Luigi Stipa claimed his in-tube propeller was the ancestor of the jet engine.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.